Okay, grade 11s. In the previous period, we had a look at the test for the anions as well as the gases. Okay, now you need to know those tests. Unfortunately, it's a little bit of learning work. Okay, now, I'm still busy with the tests, but it's got to do with the chemistry behind the tests. Okay, so in your textbooks on page 88, halfway down the page, they say the chemistry behind the tests. And they start off with the anions. And then they say, the test for a carbonate is well known. A carbonate will give carbon dioxide when hydrochloric acid is added, and this will turn lime water milky. This is always the first anion test. If you have an unknown powder, and you need to start with a series of tests to determine what is in it, the first one is to remove the carbonate, because it could complicate some of the other reactions. Okay, so you would first take out the carbonate by adding acid. They say this should be done because the anion will give a positive result in all of the other tests. Okay, so when you do a test, you add a little bit of acid to it because the acid is going to remove the carbonate. No. Okay, then they say to identify the other anions, a precipitate of an insoluble salt of the anion is made. The insoluble sulfate is barium sulfate, and we do this by adding barium chloride or barium nitrate. No. And then the insoluble chloride is silver chloride. We do this by adding silver nitrate. Are you with me? Okay, but very important when we start with these tests, then you first remove the carbonate because it interferes with the test forming the precipitate, and you will think it's maybe the hydroxide, which it isn't. All right, that's the one thing. Then I want you to turn back to page 50 in your textbooks. And this has got to do with the test, for example, with copper. We take copper ions in solution and we add, for example, sodium hydroxide to it. What will we get? Copper hydroxide, then this stuff is blue. All right? We do the second test for copper ions with ammonium hydroxide, and with a few drops, we will get the copper hydroxide precipitate, which is blue. But if I go and add excess ammonium hydroxide, when we did the cation tests, we said, what do we get? A deep, dark blue solution. Now this dark blue is due to the ammoniated complex ion. All right. Now, okay, I've got them summarized here. I'll read the bit. Okay. It's the ammoniated complex ion. This dark blue solution is due to the okay. Now, we don't go into much detail in terms of complex ions. It sort of becomes a branch of chemistry that involves quite a bit of stuff. But we do just very basically do, for example, the complex ion involved with the test for copper. All right. Now, the copper hydroxide. Let's go here. Starting off, yes. If I have white copper sulfate and I add water to it, we get the hydrated copper ion. Okay? In other words, it's going to look like this. It's still the copper ion, the 2+ ion, but it's hydrated. So this would be, for example, blue copper sulfate in solution. All right. when we add sodium hydroxide or ammonium hydroxide to it, let's take the ammonium hydroxide, we get the insoluble copper hydroxide that is formed, and this stuff is blue. Okay? When I add excess ammonium hydroxide, I get the ammoniated complex ion, and this is the copper 2 plus ion, but it now bonds onto the ammonium ion. There's 4 of them, and we have the plus 2 ion. All right. This is in your textbook. They actually put this whole thing in a bracket because the charge is applicable on the whole thing. Similarly over there. So if you go in your textbooks on page 50, I'm going to read. On the left-hand side, they say in this activity, there are 3 changes. Firstly, the addition of water to white anhydrous copper sulfate caused it to change color to blue. All right? Now, this blue liquid that we had was the hydrated copper ion. The formula for the hydrated copper ion is that one. That's the hydrated copper complex. You must know that. Then, the test for the copper 2 plus, the next step in your books, they say then a light blue precipitate was formed. But what did we do? We added a base, either the sodium hydroxide or the ammonium hydroxide. The blue precipitate that we got was this one. That is a solid. Whether it was with sodium hydroxide or whether it was with ammonium hydroxide, this was just a normal insoluble salt. Then if you go one step further with the ammonium hydroxide, when we add excess ammonium, it's as if the ammonia displaces the hydroxide. And that is why we get a soluble ammoniated complex ion. Okay? Yeah, it doesn't matter. It's in water. It's in water. So it forms ammonium hydroxide. Okay, so then just next one down, they say in the white anhydrous copper sulfate, the copper ion has no color. But when water is added, a complex ion is formed. The ligands are water molecules. What is a ligand? It's a covalent bond that is formed where one part gives both the shared electrons. Now remember, the water molecule over here, we have 2 lone pairs. So water can be the ligand. Over here, the ammonia is the ligand because ammonia, yes, has got a lone pair to form the complex ion by means of a coordinate bond. Are you following me? All right. I will read further. They say the ligands are water molecules. In this case, 4 water molecules will share 1 lone pair each with a copper 2 plus ion. Then this is shown in the equation, and they give the formula for the complex ion. And then in the next paragraph, when the ammonium hydroxide, the ammonia solution, all right. Remember I said to you, ammonia plus water forms ammonium hydroxide. All right, that is why sometimes they write it like that and sometimes they write it like that because we're in watery solutions. Okay. Yes, because the positive ion is normally written first. Carbon is usually written first. Sulfur is usually written first. That you will sort of, yeah. You know, in grade 8, I won't necessarily penalize you if you did OH-NH4. But when we get to grade 10, 11, you need to get them right. No, because water is written H2O. Hydrogen is the positive ion. Oxygen is the negative ion. It's covalent, I know. But hydrogen forms, it acts like a metal. Do you understand? Okay. There are rules in general. A lot of it is experience. Okay. Yeah, they will penalize you. Yes. Yes. There will be rules for the order. When we do organic chemistry, you'll see as well specific way of writing the compounds. Okay. I want to carry on. So when the ammoniated hydroxide is added, the ammonium hydroxide is added, the first reaction that occurs is the formation of insoluble copper hydroxide. That was this one, over there, that one. And then when excess is added on the right-hand side, just this second paragraph, when more ammonium solution is added, a new complex ion forms in which the water molecules are replaced by the ammonia molecules. The new complex is formed, it's darker blue. I'm sorry, I made a mistake over here. It's NH3. Okay. 4. So it's the ammoniated complex that forms. Then they just say in the next section, transition metal complex ions are common and some are very important to us. One example is the molecule formed when the protein molecule hemin joins the transition metal ion. Then we get hemoglobin. Yeah. Okay, this molecule is called hemoglobin and has the property of being able to form a complex when the ion shares a lone pair of electrons on an oxygen molecule to carry the oxygen. Okay. That then. Please reference this last section with a test for copper back to page 50, because it sort of actually fits in with the test for the copper, and they do it completely in a different place in your book. Okay. So take note, it's on page 50. All right. Now, at this point, I'm basically finished with the test for the different metals and non-metals and gases. We have to carry on. The next section has got to do a little bit with industrial processes. Now, the industrial processes, you need to know a little bit about them. They do ask now and again, so it's a little bit of just root learning work, which I know you love. Yeah. All right. I'm just going to go through the theory as it is in the textbook, starting off the industrial processes based on lime. Now, lime, if you heat calcium carbonate, all right, you heat it up, it decomposes, and it forms calcium oxide plus carbon dioxide. If you take calcium oxide and you add it to water, we get calcium hydroxide. All right? This one is known as limestone. This one, quicklime, or just simply lime. And this one, slaked lime. Lime water is calcium hydroxide shaken up in water. It's not very soluble, it's very slightly soluble, so you shake it up over a period of time. Yeah, and then you filter off the excess undissolved copper or calcium oxide, and that forms lime water. Okay, it's lime in water. All right, you need to know this. If you don't know it, it's very confusing. So they say there by the industrial processes, lime has been a very basic, important basic substance with many uses. Lime, however, is used in common English to refer to a number of different compounds such as quicklime, slaked lime, and limestone. You must know the difference. Then limestone rock is calcium carbonate. It occurs widely throughout the world. Was formed many millions of years ago. I don't agree with the millions of years ago, when shellfish and other sea creatures died and their remains fell to the bottom of the sea. Whatever, how they were formed, doesn't matter. Then the shells are made of calcium carbonate. And then over the years, these shells became compressed into layers. There's a whole part on geography where they talk about all these funny types of rocks that are formed and metamorphic. And no, you don't need to know that. Just know the difference between those three. Then, marble and chalk are also forms of calcium carbonate. Marble is produced when limestone has been subjected to high temperatures and pressures in the Earth's crust, which caused it to melt and then solidify again. We call this rock metamorphic rock. You don't have to know that. Some very fine quality marble is found in the hills around Karabib. Limestone is widely quarried. What is a quarry? It's a hole dug in the ground from which we pull out rocks. We quarry gravel for building, making concrete, building roads, etc. Its main use is as a building material. In the olden days, in Europe, the cathedrals, etc., were built from limestone, basically marble rock. It's not always the pure metamorphic rock, but it is limestone. And that's one of the big problems in Europe is due to the acid pollution. These structures are starting to crumble. So they've got processes, they clean it up and they put a layer over them that protects it. Yeah, I don't know if they'll cement over it, but they to try and preserve the natural structure as it was built 500 years ago, type of thing. Especially the cathedrals, it was a lot of actually specialized stonemasonry to build those things. Okay, so limestone then is widely used. And why can it be used very widely? It is easy to cut into regular shapes, okay, which makes it particularly good building structures. It's not all that, you can chip it off. Do you understand? And once you've put it into place, it's very strong under compressional forces. So it's good to use. It's a yes. Okay. They say the main use nowadays for limestone is to make cement. All right, now it's heated with clay. How do we make cement? Limestone, calcium carbonate is heated with clay. Clay consists of calcium and aluminium silicate. All right, it's heated together. Where are we now? Okay, it's heated with clay in a furnace at about 1,400 degrees Celsius. All right, it is a product of a mixture of calcium and aluminium silicates. These are in powder form when they come out of the furnace. When water is added to the mixture, the two silicates form crystals. If I take cement and I put some powdered cement, the stuff you buy in bags, I put it in my hand and I drop some water into it, it becomes hot. Why? When I've heated this up at 1,400 degrees, why do I heat it up that high? I'm trying to heat off the water of crystallization. When you add water back to it, if I put in energy to get rid of it, if I put water in, it's going to give off energy. All right, so it becomes warm. In concrete, it's the calcium and the aluminium silicate that forms long interlocking crystals if you allow concrete to dry out slowly. In our country, when you've built a new structure, you stand and you keep the concrete wet, especially in the winter. Why? Yes, because if you don't do it, the concrete will be very weak. It will crumble. Why is that? If you could look at it microscopically, you will see in concrete that has set very hard, that has been allowed to dry out slowly, it has long interlocking crystals. In concrete that dries out very rapidly, these crystals can't grow, and they are shorter and smaller, and they don't interlock as well, and the concrete becomes crumbly and weak. Okay. When water is added to the mixture of the two silicates, they form long crystals which lock around each other as they grow. If sand is added, the particles of sand are also locked into the crystal and the whole mass is very strong. We refer to this as concrete. Concrete consists of sand, cement, And water, we can add gravel to it. We can add steel bars to it. All right? Reinforced concrete. Or steel mesh in it. It's to make it stronger. But cement, the stuff you buy in the bag, is made from calcium carbonate and clay that has been heated together to a very high temperature. Okay. They say when concrete sets, it does not dry out. The water in it becomes part of the silicate crystals which are formed. In other words, if there isn't water, these crystals can't form and your concrete is weak. We refer to the water that is part of the crystal as water of crystallization. You remember when we did the stoichiometry calculations? There was one where we calculated the percentage water of crystallization. All right, it's the same thing that they refer to. We refer to the water that is part of the crystal as water of crystallization. The slower... Okay. The slower the crystals are allowed to form, the bigger and stronger they are. This is why it's important to keep the concrete wet for a week at least as it sets. Now, particularly in warm climates, particularly in dry climates. Warm, wet climates aren't a problem. But dry climates, here by us in the winter, it is a problem. Yeah. Ja, dit is hoekom hulle, as hulle dit gemaak het deesdae, dan hulle hier 'n masjiene wat dit in plastic wrap en dan spuit hulle nat en hulle vou hulle toe dat die water nie kan verdamp nie. Dan kan die baksteen groei. Dan word hy sterk. Ja, as om te keer, as om die verdamping te keer, want dit is buitengewoon erg hier by ons in die winter. In die somer ook baie, want dit is warm, maar in die somer is dit beter want daar's meer vog in die lug. En die konkreet kan die vog uit die lug uit ook absorbeer. Maar by ons in die winter is dit fataal om 'n struktuur te bou en nie nat te maak nie. Okay, alright. Then another use for limestone is a flux in furnaces for extracting metals. And when we do the extraction of metals, we will have a look at the use of limestone as a flux. Quick lime and slaked lime. Two kinds of lime are calcium oxide and calcium hydroxide. They both are made from limestone. This is a very large chemical industry. To make quick lime, the limestone is heated to over 1,000 degrees. As it decomposes, it forms carbon dioxide and calcium oxide, which is quick lime. There is the equation on page 90. Please take note. It can be asked of you to write them. I've done them. Did I do them over here? Yeah. All right. And you must know them. Then calcium oxide and quicklime does not have many uses because it reacts with water so easily that it can react with moisture in the air. It's actually very difficult to fill a bag of calcium hydroxide and leave it standing around in Namibia in the summer because there's lots of water vapor in the air. Okay. This means that it is difficult to store. It must be kept in sealed bags or bottles. Once these have been opened, the quicklime soon reacts to give slaked lime. All right. It has a rather unpleasant property that it reacts rapidly with living or dead animal matter and must therefore be handled with great care. You mustn't breathe it in, for example. Because of this property, it is used to destroy diseased animal carcasses, such as cattle, etc., that have been slaughtered because they are diseased. I can remember, this is about 20 years ago, maybe even longer. Daar was varkpes onder die varke hier rond. En toe het die ouens gate gegrawe en die varke daar ingegooi en quicklime oorgegooi, né? Covered them up and just extracts all the water from it. No bacteria can rot and grow further. It's to stop the diseased carcasses, the diseases from spreading. Then, three main uses of calcium hydroxide are as a fertilizer. Why would we use it as a fertilizer? The plants don't need to take it up. Is it acidic or basic? It's a base, a metal hydroxide. So when soil becomes too acidic, we can add this to the soil. It lies in the soil, it's inert, but when it rains and it becomes wet and there's an acidic medium, it will react and neutralize the acid. Okay. A fertilizer, it's used for making sodium hydroxide from salt in the alkali industry and for neutralizing acidic industrial waste. And then there's a flow chart of the limestone industry. There's a part on the alkali industry. They refer to the Solvay process. Now, the Solvay process, people, in your syllabus, they specifically refer to the Solvay process. They have never asked it in all the years to describe it from beginning to end. At best, they ask 1 or 2 marks on it. It's a section of work that I personally don't like because the Solvay process differs slightly from one place to another. Okay? So during the Solvay process, if you look on page 91 on the right-hand side, it uses calcium carbonate and sodium chloride to make sodium carbonate and calcium chloride. All right, so ions are swapped around. Unfortunately, this reaction does not happen easily, and it is done in several steps. Step 1, calcium carbonate is heated. You have to go and learn this. There's no way beyond it except learning it out of your head. But if it's really hard for you to go and learn this, because even if I had to go and sit and write it down, I'll make mistakes. I don't work with it often enough, no. Okay, and they have really never ever asked anything much on the Solvay process. So if you reckon it's worth a chance and you don't bother with it, then you don't. But just know it is part of the syllabus, okay? So step 1, calcium carbonate is decomposed into calcium oxide and carbon dioxide. Step 2, ammonia and carbon dioxide are bubbled through the salt, giving sodium hydrogen carbonate, which is not very soluble, and it crystallizes. Step 3, the ammonia is recovered for reuse. Step 4, sodium hydrogen carbonate is heated to give sodium carbonate. They recover the carbon dioxide for reuse. All right. And then there's a flow chart, all the different uses of these substances. You need to know 1 or 2 of the uses. Okay. Then, sulfuric acid industry. Now, there are 2 other industrial processes except for the Solvay process. We talk about the contact process, and the other one is the Haber process. The Haber process we did in grade 10, somewhere. Okay, we will redo the Haber process. The contact process is the process that they use to make sulfuric acid with. Sulfuric acid starts out with sulfur that is burnt to form sulfur dioxide. All right? The sulfur dioxide is oxidized further to form sulfur trioxide. And if we add sulfur trioxide to water, we will get sulfuric acid. Although it's never just as simple as that. Okay? There are some particular problems that we experience with this reaction, and I'm going to just go through the book as it is written there. So on page 92, we will start with, just start at the top. Manufacture of sulfuric acid, one of the biggest world chemical industries, all right? Sulfuric acid is a chemical from which many other useful materials are made. It's a heavy, extremely corrosive liquid, which causes burns, etc. You have to be very careful when you handle it. The reason why it's so dangerous to living tissue, and not because it is an acid, but sulfuric acid specifically is an excellent dehydrating agent. The experiment that I do with the sugar and the sulfuric acid, and it burns the sugar, okay? What it basically does is it removes the water. Sugar is C6H12O6, so there are 6 water molecules in it. And that is what the sulfuric acid does. It removes the water from the molecule. And that is why it makes rubber brittle if it's exposed to a lot of sulfuric acid. It eventually removes the H2O from the molecule. And the rubber becomes brittle. Okay, we will start with the contact process next period. grade 11s, we are almost finished with this chapter 5. We have to, I think we were busy with the contact process when the bell went in the last period. Okay, so it's industrial processes. You definitely need to know the contact process, and then when we do another section of the work, the harbor process. All right, contact process, we already said it is sulfur that is burnt in oxygen to form sulfur dioxide, and then the sulfur dioxide is oxidized further with oxygen to form sulfur trioxide, and when we add sulfur trioxide to water, we get H2SO4. But once again, people, in practice, nothing is as simple as it seems. All right, so in your textbook, there on page 92, there we have the sulfuric acid industry. Now, sulfuric acid, people, industrially is a very important chemical. They use it in mining. I know, for example, the sulfur dioxide gas that is a pollutant in Shumep, they've started catching it up and converting it into sulfuric acid. This is taken with lorries to the gold mines and the uranium mines in Swakopmund, where they use sulfuric acid as part of the extracting process. All right. So, the manufacture of sulfuric acid is one of the biggest world's chemical industries, okay? Millions of tons of acid was made in 1990. We are, how many years? 30 years down the line, there will be more. All right, so it's a very important chemical. The reason why it is dangerous, I think this is where the bell went. We said it is a dehydrating agent. In other words, it removes water. And that is how we explain why rubber becomes brittle. Because rubber is actually a hydrocarbon. There are other elements in it, and it's got a special structure. But when it's exposed to sulfuric acid specifically, the sulfuric acid has the ability to remove hydrogen and oxygen in the form of water. Okay, and it would be a similar reaction to what we have with the sugar, where we add sulfuric acid to it. Remember, sugar is C6H12O6, all right? So if I take out the carbon, can you see there are H12, okay. That's why I couldn't figure it out now, okay. How many water molecules have we got there? 6. Can you see that? So for every one sugar molecule, the sulfuric acid boils off or dehydrates, removes 6 water molecules. Okay. Now in rubber, it's maybe not 6 molecules, but over a period of time, it goes a little bit slower, but eventually the rubber becomes brittle and it breaks because the molecule is being broken down. Okay. Sulfuric acid, yes? Yes. No, but if there's lots of pollution in the air, remember there are other weak acids in the air that will do similar things, but it just goes longer. All right, and some of them are they are sensitive to ultraviolet rays as well, so that also can do damage. Okay, yeah. Yeah. I know the carry bags at one stage were designed to allow ultraviolet radiation to cause them to break up into small flakes, because then it's easier to break down a smaller molecule than a bigger one. So ultraviolet radiation causes the bags to become brittle and break. So that would also play a role then. Okay, so sulfuric acid is made from sulfur dioxide gas. Where do we get the sulfur dioxide gas from? They burn sulfur. Sulfur can be ground up into a powder. It's a yellow substance. It's fairly freely available. It's not really a very expensive reagent. If you go to Agra, you will get pots of sulfur, blomswal, on the shelves. They use it for animals and for whatever. Okay. It is sulfuric acid is made from sulfur dioxide gas. The sulfur is obtained from deposits. It's mined from specific places. The first reaction, we've got it on the board. Sulfur plus oxygen gives us sulfur dioxide. If you look at the flow chart on the bottom of the written part, then you will see the first section is sulfur and air goes into something called a sulfur burner. It's just a chamber in which air is blasted through it so that the sulfur can burn in the presence of oxygen to form sulfur dioxide. The sulfur dioxide is taken into a next place where they have a contact process. Now, the word contact process is we need a catalyst, because now we have a gas, and to make one gas react with another gas, it will occur easier if they can find each other on a surface. Okay, so there's a catalyst. It helps the reaction along. Now, the catalyst in this case is vanadium 5 oxide. You need to know the catalyst. If you write it in words, it's simply if you look at the formula, vanadium, what's the formula for vanadium? V, just a V, the A. Vanadium oxide, how many bonding places does vanadium have? 5. How many bonding places does oxygen have? 2, so V2O, 5. Okay, do you follow? All right, so the catalyst is vanadium 5 oxide, one of the transition metals. What is the use of a transition metal? Often they are used as catalysts. No. All right, then the next step, the sulfur dioxide is first converted into sulfur trioxide by mixing it with oxygen and passing it over a catalyst at about 450 degrees Celsius. Now, one of the parts of work that you have to do next year has got to do with rates of chemical reactions. And two of the factors that influence rates of chemical action, one is temperature, because the more energy particles have, the more they can move, the more they can collide, the greater chance of a reaction. And another one is a catalyst, and catalysts help reactions along. Now, how they do it, we will have a look at that when we do rates. But at this point, take note, you need to know that the contact process, the reaction between the sulfur dioxide and the oxygen, occurs in the presence of a vanadium 5 oxide catalyst at approximately 450 degrees Celsius. Okay. When we do rates, we'll come back to this contact process again to see how these factors influence the rate. Okay, so the next section then there, they say the catalyst is the oxide of the transition metal vanadium. So this process then is called the contact process, because these two substances need to be in contact with the catalyst. The sulfur trioxide produced in this way must be added to water to make sulfuric acid. But now we have a problem, because when I take sulfur trioxide and I add it to water to make sulfuric acid, this reaction is extremely exothermic. It gives off loads of heat. And what happens is it tends to vaporize the sulfuric acid. Now, vaporized sulfuric acid at 450 degrees Celsius is a recipe for trouble. All right. So what they go and do, and that's the next step there in your textbooks, they say the sulfur dioxide produced in this way must be added to water to make sulfuric acid. However, this process produces much heat, okay, and is easier, well, and safer to dissolve it first in concentrated sulfuric acid. So what they go and do is they go and absorb this produced sulfuric acid, hydrogen sulfide, in concentrated sulfuric acid. Okay, and the substance that they get then is called oleum. Where? Is it right? Yeah. This whole reaction is absorbed in. Okay. So they don't add the stuff to water. They add it to sulfuric acid. Okay, remember sulfuric acid does contain water. Then the reaction, well, is more containable. Okay, it is still exothermic, but not as violently. Now this oleum is a thick liquid. If you get a bottle of oleum, you'll not think that it is sulfuric acid. It's a thick liquid. It's got the consistency of oil. It's thick. You can pour it. It looks like an oil, and it's slightly yellowish in color. To make sulfuric acid from oleum, what would we have to do? Yes, add water. Okay, and then it will ionize and it produces sulfuric acid. When you add the water, you never take your bottle of oleum and add the water to the oleum. Okay? You do it the other way around. You can control the amount of oleum that you add, and you'll do it very carefully because it will become very hot. Okay? Now, the sulfuric acid that we buy in the laboratory is not in the form of oleum. It will be a highly concentrated sulfuric acid. Okay? It is, well, the formula for oleum is H2SO4, but it's just a very concentrated sulfuric acid. Okay. Yes, yeah. So I think if you start out and you don't have, then you will do this first exothermic reaction until you have a certain amount. And from there, you will go and absorb it in that, okay, because it's less dangerous. All right, so then you will see in the flow chart, they've got the contact process, which is with a vanadium 5 oxide catalyst, right in there, 450 degrees. That's on the second block. And then from there, the sulfur trioxide reacts further, it's oxidized further with oxygen, and it is absorbed in concentrated sulfuric acid to form oleum. And oleum, when it's diluted, will form concentrated sulfuric acid. All right. That is the end of that section of the work. I'm going to stop the recording and we'll start a new one for the next section.
Namibia ice. Did I get sister Hulda Navasida? Did I get I Hoa? Namibia Oncology Center Naragrasisen. I come from Ti Quedo. Bounce a hari. Omsnahari. Oma Badanahure. Nugu said again ha ugu. Habe I get off Nugu said ha ugu habe. Han are ugu ha. Hoge bounce a hari. Ida tadi nedi I 2019 novel coronavirus sting higusa. Au bounce a hari.
Hi, welcome to the program. I'm Debula. So let's get on the road with this. Having someone who likes what you like can be great. It gives you something to chat about and share with each other, yeah? But what if you both want to be at the very top of what you're doing and your main rival is your brother? Can you imagine?
Mount Nyiragongo, located in the Democratic Republic of Congo, is one of the most active volcanoes in the world. It's found in the Virunga Mountains and located 6 miles from Goma. So what caused Mount Nyiragongo to erupt?
This is Women in African Music virtual exhibition. It was created by the British-Nigerian documentary photographer Michael Tubes.
Women in African Music exhibition is about celebrating our women behind the scene and our women performing on the stage.
This fishing community on Mozambique's northern coast has been hit hard. People here are suffering from high rates of malnutrition, but that's not all. The greatest concern is the high rates of HIV infection and AIDS, the main cause of death in adults and young people across Mozambique. Poor nutrition makes it even more difficult for people to fight the disease. 21-year-old Elima Artur is the daughter of one of these fishermen. A few years ago, she suddenly started suffering from an unknown illness.
Me encontrei eu desesperada, totalmente triste, minha vida só era chorar. Pensei que eu já estava a ir já.
All this changed the day Elima met Arlek Anna Abel from a project called Chapani. With support from IFAD, the International Fund for Agricultural Development, and the Belgian Fund for Food Security, staff from Chapani work with villagers to combat the dual threats of HIV and malnutrition. When Elima tested positive for HIV and AIDS, Arlette encouraged her to form a support group. Elima chose her father and aunt, who helped her to stay optimistic and healthy. In fact, teaching people to eat well is an important part of Arlette's work.
Eu ensinei elas para que pudesse enriquecer os alimentos para ela poder as hemoglobinas não baixarem. Então, já se alimenta agora de verduras, não só do peixe.
As part of the Chapani project, cooking demonstrations are held for everyone in the community. The session today features the highly nutritious moringa plant, a fast-growing, drought-resistant tree unknown to many locally. Now it has become a popular item in the local cuisine. Maria Machambi, who is not HIV positive, is learning to create her own garden with more than 6,000 other families in the area. The idea is spreading quickly throughout the community, with locally trained volunteers now leading the process.
They share their ideas with their neighbors and everyone gets excited. For us, that is key. Once communities own the process and they don't need an external person to tell them how to cook food, how to prepare it, they do it within themselves.
The success of the project has motivated IFAD to expand nutrition education across the nation over the next 3 years. Meanwhile, Elima is playing a key role in spreading the word about healthy living. Through songs, she informs people about safeguarding against HIV and AIDS, adopting healthy eating habits, and learning to cope with the disease.
Vê lá, me repara só. Sabe, uma pessoa pode me ver, não saber que eu tenho esse tipo de problema. Hã? Estou bem, hein? Viste?
And with more than 10% of Mozambique's adult population infected with HIV, this message has never been more pertinent. This report was produced by Jonathan Elliott for the United Nations.
The coronavirus that causes COVID-19 has changed since the pandemic started. So does this mean the virus has become more dangerous? Scientists have discovered thousands of mutations to the SARS-CoV-2 coronavirus. Most mutations only lead to small changes, but scientists believe one, called D614G, may have made it easier for the virus to infect human cells. This mutation most likely emerged after the initial outbreak in China, and it spread fast after the virus arrived in Europe. By the end of June, the D614G mutation was found in almost all samples of the virus worldwide. Scientists believe this is due to amino acid changes in the virus's spike proteins, improving its ability to infect human cells. Some studies have found more spikes on viruses with this mutation. These spikes latch onto receptors on the surface of our cells. They then transfer the virus's genetic material, called RNA, inside. Being inside the host cell allows the virus to make many copies of itself. Random errors sometimes happen in the copying process, which cause mutations. Although the full effects of D614G are still unclear, some studies suggest that the mutated virus might be more transmissible than the original. This could mean more people getting sick and at a faster rate. Despite this, there isn't any evidence that the disease itself has become more severe. Scientists are worried about mutations possibly increasing the risk of reinfection. Hong Kong reported what could be the first case of virus reinfection on the 24th of August. A healthy man in his 30s is thought to have caught the virus again 4.5 months after he first got sick. During this time, mutations developed and new variants of the virus emerged. Some experts believe these changes may have made reinfections more likely. Mutations are common over the course of a pandemic. New flu vaccines are needed every winter to keep up with genetic changes to the flu virus. If a coronavirus vaccine is found, it could require regular booster jabs. Mutations won't happen overnight, and the coronavirus is mutating slower than the flu virus. But it's important for scientists to keep a close eye on how the virus changes over time. Could we be hearing more about other mutations in the future?
The mighty Zambezi River, the longest east-flowing river in Africa, a river that flows through 6 countries, home to a plethora of wild species of fauna and flora, a lifeline for many people whose livelihoods are dependent on the abundance the river brings. Globally, communities who live along rivers rely on these rivers to survive. Communities living along the Zambezi call it the river of life, bringing water for their crops and fish as their main protein source. In Namibia, a country situated in sub-Saharan Africa, the Zambezi River sits at the heart of Kaza, the Kavango-Zambezi Trans-Frontier Conservation Area, which is one of the greatest conservation areas on Earth, a stronghold for very many of our most iconic wildlife.
I'm right now where the river forms the border between Namibia and Zambia. This enormous water body provides sustenance to a wide array of wildlife, bird and fish species. It's also a lifeline for human beings.
The same communities are the people also who are doing the illegal activities.
The price of fishing has gone up because fish has become scarce.
The more they finish us, the more our life gets harder and harder.
These days, it is very rare to get a big bream unless in those protected areas.
A small group of community members, together with non-governmental organizations like Namibian Nature Foundation, are fighting back.
We have to start thinking out of the box, to be honest, because what's going to happen is going to be out of this box that we haven't seen before.
By creating protected areas, monitoring and patrolling, fish stocks have a chance at recovery. These are the stories of the people fighting for the continued existence of their communities. These are the last defenders.
Struggling with no food, no what. But we didn't stop. If we are going to do it, our young children, they'll never know the fish.
A very big hello to you, ladies. It's great to be with you on the show again.
Yes.
Welcome to Living the Life.
Marriage is where the work really is.
That's the main. So no matter how exhausted the event planner is after, oh my God, I did such a beautiful wedding. She did the wedding. That's not the work. You understand?
The work is the couple now.
The uterus begins to shrink back to its normal size. It takes about 4 to 6 weeks for it to get down to below the umbilicus level, and 4 to 6 weeks if you're breastfeeding. So that's another incentive to breastfeed.
Oh yes.
You're wondering, love, what does it really mean? Someone is telling you, I love you. But if you love me, show me that you love me.
Investing in marriage takes a real hard work. It's not something that you just wake up and feel like, no, because I married my best friend. It's not automatic that the marriage is going to work.
Akili, 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 akili. Water, water, wash your hands. Scrub with soap, wash your hands. your dinner. Wash your hands before you start to munch. Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe. Wash your hands after using the toilet. Wash your hands after you sneeze or cough. Wash your hands after you touch animals. Wash your hands to wash all the germs off. Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe. Wash your hands before you eat your breakfast, before you eat your lunch, before you eat your dinner, before you start to munch, after using the toilet, after you sneeze or cough, after you touch animals, to wash all the germs off. Wash your hands! Water, water, wash your hands. Scrub with soap, wash your hands. Front and back, wash your hands to be clean and safe.
More than ever before, football fans demand unique insight and analysis. The Football Review is much more than a highlights show. Bold, provocative editorial that goes beyond conventional reporting, setting the agenda for football discussion. Champions League, Premier League, La Liga, Serie A, Bundesliga, Liga 1, and much more. Want genuine insight with hard-hitting editorial? Need compelling premium football content? The Football Review. Best bar none.